Morning, guys. We're going to go over some momentum predictions, a little bit of momentum notes, and see if we can relate our previous knowledge to what the next section is, which is going to be momentum, impulse, conservation of momentum, and center of mass. All right, so first off, we're going to start at the same place we always do with some vocabulary. We have two different types of collisions. We have an elastic collision and an inelastic collision. In physics, an elastic collision means that our energy is conserved. So our initial kinetic energy is going to be equal to our final kinetic energy. An inelastic collision, as you could probably guess, means that it's not going to be conserved. So our initial kinetic energy does not equal our final kinetic energy. This energy is going to dissipate in similar ways that it did in the previous section. Very often, momentum and energy are taught together because they have a lot of things in common, but you're going to see this energy transferred mostly into heat. But it can also go into sound, it can go into distortion of the objects, like the objects actually changing shape. Impulse is going to be the change in momentum. The Fosbury flop is going to come up in the center of mass. This was a new style for the high jump. And then center of mass is going to be the point we can consider all the mass to be. So we've done this indirectly already a couple times when we talk about the force of attraction between us and the Earth. We consider the mass of the Earth to be dead center of it. So we could say that all of the mass, all 5.9 times, or 5.98 times 10 to the 24 kilograms is all at that point. All right, so I want to make some predictions about some collisions. So we're going to start with the executive toy. I'm going to pause you guys and change the perspective. All right, guys, I'm back, and we're going to look at this Newton's cradle. So the first thing we're going to want to do is make a prediction. What's going to happen when I just displace one of the metal balls? Interesting thing about this Newton's cradle, they all line up in a row. They're all of equal mass, which is unusual for things that are colliding. Normally one thing is going to be more massive than the other. All right, so the first thing is you're going to make a prediction. What's going to happen when I pull one ball up and release it into four? Do you think that the ball will just bounce back because it's less massive? Do you think that two balls will go up? Do you think all four will move a little bit? Do you think just one ball will go up? And it turns out that just one ball went up on the other side. All right, the next one is we're going to displace two balls together. And I'm interested in what's going to happen when I release it. So I displace two together and I let them go. And it turns out that now two have gone up on the other side. So I put one up, one went up on the other side. I put two up, two went up on the other side. Now I'm going to put three up. When I put three up, there's not going to be three down anymore. There's only going to be two. So what do we think is going to happen when they go up? All right, three up. And it turns out that when three go down, three go up on the other side. All right, so in the notes it's asking how would I describe the forces between the balls as they collide. So does the first ball hit the second ball more than the second ball hits back the first ball? And the answer is no. Their magnitudes would be equal. So when I displace this and let this go and let it down, the first ball hits the second ball exactly as hard as the second ball hits the first ball. It hits it just enough to stop it. Then the second ball hits the third ball hits back on the second ball just hard enough to stop it. The third ball hits the fourth ball hits the third ball just hard enough to stop it. The fourth ball hits the fifth ball hits the fourth ball just hard enough to stop it. And then there's nothing for the fifth ball to hit. It is displaced, and then it continues over and over again. All right, last question on this is, does this continue endlessly? And the answer is no, it doesn't. So why? We are losing energy in the system. If we had a way, if we could measure these balls, they would be slightly warmer after these collisions. The fact that you can hear this means that there's some sound energy generated. So to demonstrate this, I made a purchase out of a catalog, not one of my better purchases. And the idea was that we had these very heavy metal spheres that I'll bring them around closer. And the idea was that these were so massive that if you smashed them together, the energy generated, the heat that was created, would be enough to light a paper on fire. And the graphic, and I should have known that the graphic was misleading me because it was like a cartoon graphic, but the graphic showed this piece of paper lighting on fire, and I thought, this is going to be great. I'm going to do this demonstration. I'm going to smash these together. This piece of paper in my hand is going to light. Everyone's going to be impressed. They're going to clap. It's going to be like Dr. Walter Lewin. And the best that I could get, and I tried this with the other physics teacher next door. We tried flash paper. We tried filler paper. We tried tissue paper. We tried paper towels. The best we could get is if you smash it together and then smell it, it smells a little burnt. That's the best that I could get on that. So that was a little bit of a disappointment in that. All right, so we're going to move on to the billiard ball and the ping pong ball. Hopefully you're able to see. So I have a number of different balls up here. I'm going to put these off to the side so they don't distract us. But I have a clay ball and I have a lacrosse ball that are of equal mass for later. So I am going to collide two things that are of very unequal mass. I have an 8-ball and I have a ping pong ball. So I want you to make a prediction. What will happen when I release the billiard ball to hit the ping pong ball? So when we did it one equal mass, it pretty much went to the equal height. Is the same thing going to happen here? And then what do you think will happen to the billiard ball after it hits the ping pong ball? What do you think will happen to the ping pong ball after the billiard ball hits it? All right, so I'm going to let it go. And if you notice, the ping pong ball, if you just watch that, goes way higher. The billiard ball, if you just watch that, it's almost like nothing hit it. All right, I'm going to switch it around. I'm going to let the ping pong ball hit the billiard ball. Make a prediction about what you think will happen when I do that. Feel free to pause the video to write that down in the notes. Oh, not a straight on shot. Here we go. So when the billiard ball hit the ping pong ball, the billiard ball kept on going, the ping pong ball went much higher. When the ping pong ball hit the billiard ball, the ping pong ball rebounded, and the billiard ball moved just a little bit. Which ball hit the other with more force? The answer is neither. They hit it with exactly the same. To which ball was that force a bigger deal? It was a much bigger deal to the ping pong ball. So that's why the ping pong ball went to a higher height, because that force was a bigger deal to its mass. All right, so I'm going to switch things up. I have a piece of clay and a lacrosse ball that are of the same mass. The lacrosse ball is a little bit bigger. It's a little bit less dense, but they're the same mass, and I want to collide them. And I'm going to displace the clay ball and let it hit the billiard ball. And I want you to make a prediction about what is going to happen when they collide. So do you think the billiard ball will go to an equal height on the other side? Do you think that the billiard ball will make the clay ball go back? Do you think the billiard ball will stop at the bottom? Anything like that. Feel free to pause the video if you feel like you need to. All right, 1, 2, 3. All right, I'm going to switch it up and do the lacrosse ball. Go ahead and make your prediction. I'm going to displace it to the same height and let it go. And a way different result. So, why did the lacrosse ball stop and make the 8 ball go up to almost an equal height? Why did the clay ball hit the 8 ball and kind of just go up with it? I got my strings crossed. It has to do with the collision itself. So the clay ball, when it hits the billiard ball, it changes its shape. It's clay. It has the ability to take on all sorts of different shapes. The lacrosse ball wants to be round. So when it hits the billiard ball, it also changes shapes, but it wants to get back to its original shape. So what happens is that it exerts a force on the billiard ball as it's changing shape, and then as it's going back to its original shape. So it bounces the billiard ball off to almost an equal height. The clay ball changes shape and then just stays with a dent in the side. And so it just continues to go on. It does not have that restorative force to get back to its original shape. All right, I'm going to relocate you back to the original location. All right, I'm back, and it's getting to be almost 7, so it looks like I'm going to have to do the second half of these demonstrations during my planning period. So this will be 2 videos for you guys to look at. All right, you might have seen this one. It's a very famous physics demonstration. We have 2 things, very much like the lacrosse ball, that if you change their shape, they want to go back to their original shape. I have a tennis ball. I'll drop it from eye height. Not a brand new tennis ball, so it's a little bit less than my waist. I have basketball. It drops from my eye height a little bit above my waist. So what do you think will happen if I drop the tennis ball on top of the basketball from the height? I'm going to put you guys back a little bit so you have a better view of how high it goes. So, putting this on top means that they're going to fall at the same rate, right? It's the same way I took out of air resistance when I dropped the book and the piece of paper at the beginning of the year. So they're going to fall down to the ground together. How do you think that they'll bounce up? All right, 1, 2, I should move forward a little bit from my projector. 1, 2, 3. So it turns out that it hits the ceiling. Why would that be the case? Well, this is a more complicated collision than the billiard ball and the lacrosse ball or the billiard ball and the clay ball. Why? Because we have an added thing in our collision, which is the earth or the floor in here. And so what happens is, as these go down and get down to the ground, we have a collision between the basketball and the ground, which changes the shape of the basketball a little bit. The tennis ball and the basketball, which changes the shape of the tennis ball a little bit. And then when the basketball goes back to the shape it wants to go to, the force between it and the ground is a much bigger deal to the basketball. And then when this changes shape and goes back, the force between these two is a much bigger deal to the tennis ball, and so I get this launching off. And that took off through the classroom. All right, I think I'm going to pause here. We're going to look at a couple more collisions between things of equal mass and unequal mass, but I feel like I need the rest of the morning to get ready for second period, so we'll have 2-part videos.